can't speak any Polish, so I'm not even going to attempt to say hello or anything like that. What I'm going to do is talk about packet core network evolution, but before I do so, I'm going to cover some of the general trends we're seeing in networking today, the architectures that we have out there, and the things that are actually going to drive future network sort of directions. One thing I would say about this presentation is I'm going to concentrate primarily on the evolution of packet environments. There are other environments out there. There's TDM, there's private line services. I'm going to mention those as I go through, but the main consideration of this talk is how we see the packet core evolving and what's going to be involved with it. So just as an introduction, we are seeing a circuit to packet migration. This chart here is a chart that was done by ACG Group about a year ago, looking at how service providers saw the traffic on their network and the proportion of traffic in the TDM space and the IP space. And what they found is that today there's a very big variation. You know, if you go and speak to someone like Google, they'll say, well, I've got 100% IP traffic. Whereas if you go to sit and speak to someone like AT&T or a more traditional service provider, they'll say, well, I've got a lot of TDM traffic. So there's quite a big variation. But what the sort of situation today is that private line sort of overall is 50 to 70% of the traffic, and IP sort of packet-based solutions are 30 to 50% of the traffic on a sort of survey of 10 or 15 major service providers. What we're seeing, though, is a major change over the next couple of years, and the change is absolutely universal. So rather than there being sort of some service providers saying, well, we do a lot of TDM today and not very much packet, the change, as I said, is universal, and by 2016, 90% of all traffic flowing on networks will be IP packet-based traffic with sort of 0 to 10% TDM-based type traffic. So a very, very major change in terms of the traffic profiles. And one of the things that means is that people have got to design their networks for this change. If I design the network for the status quo today, I am going to get it wrong. I need to anticipate that there is going to be a vast amount of packet traffic in the network and comparatively small amounts of TDM type traffic. In addition to that, we're also seeing a shift of the SP revenue from circuits to packets. And it's happening in two ways. One is the obvious way. Well, the PSTN traffic and the revenue from it is gradually going down, and service providers are making more out of the broadband infrastructure. But we're also seeing traditional services beginning to shift onto packet technology. So really the best example is the mobile world. The mobile world traditionally has been based around TDM technology, so E1s, T1s, ATM, frame relay, and the next generation, LTE, is an entirely packet-based solution. So we're going to see a complete sort of technology shift in the mobile space to go on to packet solutions. And as a consequence, the revenue associated with that sort of traditional, TDM solution is going to be packet-based in the future. And I'm sure if you've ever been to a Cisco presentation, we quote numbers at you about, how packet traffic is increasing. I think at the moment we're projecting about 34% compound annual growth across the world, but actually, if you look in pockets around the world, that growth rate can be significantly higher. So this is really the background that we need to sort of consider when we look at how we're going to evolve the architectures of SP networks. So a hugely stylized picture. what does an SP network look like today? Well, at the base of the network, what the network runs on, we have basically point-to-point 10 gig DWDM systems. And they provide the technology for the transportation of TDM or packet solutions. We tend to see, and I've got a slightly different picture of this in a second, but we tend to see that the metro networks are layer 2 based. And in the sort of where I come from, UK, they have been ATM and they're transitioning across to Ethernet. I suspect that you guys missed out the ATM piece and went straight to Ethernet. But we fundamentally have a layer 2 infrastructure that goes from the IP edge down to the actual customer themselves. We have core routers that I'll call them generalized, and I'm going to talk a bit more about core routers later in the presentation. But the concept behind the core router was that I build this device that I use in the core to start with, and I gradually migrate it to the edge as the performance requirements of core routers increases and as the requirements of the network increase. We have multiple levels of hierarchy in the network, and as I said, this is a highly stylized picture, but it's actually based on a European service provider, not a UK service provider, but a big European service provider, where they had, in the past, they had an inner core, they had an outer core, and then they had the regional network or the regional components that sat outside it. So the network consisted of sort of multiple layers of onion skin as we went out from the core of the network. We had very centralized peering and data center infrastructures. So 1 or 2 peering points per country and perhaps 1 or 2 data centers per country. So the traffic kind of moves up through the network to these points. We have an IP/MPLS control plane, typically, and then in terms of the technology that's connecting everything together, we're tending to see 10 gig on POS connections, packet over SONET connections today, and certainly the bigger service providers have pretty significant bundles of 10 gig connections, so sort of over 30 in some cases. And then the traffic goes from those routing devices via static gray interfaces down to the DWDM layer. So a very quick picture of what the network looks like from a stylized perspective sort of today. Another way of looking at it is sort of on a sort of cross-section basis in terms we have a core, we have an edge, that's where the IP and layer 3 services live. We then have a layer 2 component in the aggregation, and then we go down to the access nodes either via MPLS technology or primarily Ethernet technology, and then we actually have the customers that sit down below that. And then again, a slightly different way of looking at the picture is that what we have in terms of sort of OSI, sort of stacky type pictures, we have a DWDM layer, we have IP/MPLS technologies going directly down to that DWDM layer. We have a pretty significant SONET SDH component that again goes down to that DWDM layer, and we have a frame relay or ATM or any of those other technologies that utilize the SONET SDH infrastructure. So what we need to do is to think how that lot's all going to change. And before I discuss that, I think it's a very good idea that we look at some of the architectural drivers that we see out there and some of the technology drivers that we see out there. So let's talk about technology drivers to start with. So from the past to the future, the DWDM layer is going to become much, much more agile. So today, DWDM is fundamentally point-to-point connections, and if I want to provision a connection between city A to city B, and I go through an intermediate node, then I typically use a patch cord or something or a regenerator to get the traffic to go through that intermediate node. What we're seeing in the DWDM space is that the photonics layer is becoming switchable in its own right. So we can switch lambdas at intermediate sites using ROADMs. We're also seeing the client interface to the DWDM infrastructure becoming much, much more flexible. And the first point is that the transponders are becoming colorless, so I can tune them. But the really important bit, I mean, that's a prerequisite, but the really important bit is the entry point into the DWDM infrastructure is becoming flexible as well. So if I change color on the transponder, I don't need to replug the interface into the ROADM infrastructure. The ROADM infrastructure can take different colors and it can switch out in either direction. So the client interface is becoming more flexible. We're seeing coherent technology coming in with 100 gig. What's important about coherent technology is, first of all, it gives us 100 gig, but it also makes the engineering of the optical photonics infrastructure much easier. And as a consequence of easing of the engineering, the flexibility of the infrastructure, it actually now makes sense to have a control plane at the optical layer. So we are seeing vendors putting out control planes at the optical layer, and they are typically GMPLS based. So if you look at a Cisco ROADM solution or Cisco Photonics solution, we have the ability to run GMPLS and allow you to set connections up across the network. And in the future, we expect flexible spectrum coming along. So we have, rather than having a fixed grid spectrum where we can only, we have a certain amount of spectrum for each connection, we expect that to become flexible. So we anticipate an environment that is really much more agile in nature, supporting 10, 40, 100, and then the next sort of generation bandwidths beyond that. So what we have there is really a flexible lambda switching layer. Next thing we need to think about that's come along in the last couple of years is OTN switching. OTN switching, optical transport networking switching, is part of the G709 standard. There are two parts to G709. One is about putting traffic onto the DWDM infrastructure, and you can think of that as the digital wrapper component of OTN. The second component of OTN is really a multiplexing hierarchy, a TDM multiplexing hierarchy, really sort of SONET SDH on steroids, and it is an optical electrical function that allows us to switch containers around the network, and those containers go from ODU 0, 1.25 gig, up to ODU 4 today, which is 100 gig. And we have a flexible hierarchy around the network. And in terms of what it does sub-lambda TDM switching effectively. Then we have routers and packet equipment. What we're seeing in that space is that, like everything else, routers and packet equipment are following Moore's law. So they're getting faster, they're getting cheaper, they're consuming less power per gigabit. But what we're also seeing in the core router space is we're looking at building sort of either dedicated boxes or line cards for specific functions. So rather than having the generalized core router that we had in the past that had every edge function you ever wanted on it and you could move it to the edge, the actual core routers today, either based on an entire box or based on line card sort of selection, allows us to build more optimized core routing solutions. So what we're seeing is that core routing costs are actually going faster down in terms of cost than perhaps Moore's law would suggest. We have MPLS technologies. So we have MPLS TP about transport-orientated services, but equally as important, and I think actually more important, looking at the way the world is moving, we are making some really major strides in building very, very large-scale IP MPLS environments. So the seamless MPLS stuff that came out of Deutsche Telekom a couple of years ago, the unified MPLS stuff, which is coming out of Cisco at the moment, provides the ability to build really, really large IP MPLS infrastructures, so thousands, tens of thousands of nodes. And we're also seeing the integration of IP MPLS and MPLS TP environments. So taking the OEM type functions that came out of MPLS TP and applying those into IP MPLS environments to basically enhance the overall offering. And then the last piece, let me just fill in the picture bit. The last piece is the sort of computer technology. We're seeing the virtualization of computing resources, cloud computing, data centers, and all of that kind of stuff. I'm not going to dwell on that hugely today, but that's actually giving us a number of opportunities, and it's also changing the behavior of the network. It's changing the nature of the network in terms of where traffic goes and comes from. But it also gives us, in the longer term, the ability to perhaps virtualize some of the network functions. So rather than having dedicated appliances to do things, we might be running those in the data center as a virtualized network function. So let's now talk about traffic patterns. The traditional traffic pattern has been from the edge to the right of the center of the core of the network to the peering points, or the SP sort of data centers around the network. With the advent of things like distributed data centers, with the advent of increased levels of peering, we are beginning to see a slightly different traffic pattern. It may not apply everywhere, but it's certainly something that we're seeing in the US providers. They're putting much deeper peering points within their networks, actually European providers as well. They're putting much deeper peering points within their networks. They are putting data centers much further out in their networks. So rather than having this sort of access to core demand, we're actually seeing demands beginning to go north, south, and east, west as well. So we see situations like that. And I'm sure that you can't see this graph at all from where you guys are sitting. I can barely see it. But this is actually a chart showing the degrees of peering. And what the blue line is showing, if I can see it, is the actual content providers. And basically they're missing out the guys, the sort of level 3s and those guys, the big sort of tier 1 providers, and actually going down and peering with the guys that actually provide the access to the customers. So we're seeing a richer peering infrastructure developing. Let's now have a quick look at what we're seeing in the fixed line world. What we're seeing in the fixed line world is that the first iteration of video that went out in the fixed line world completely got it wrong. And I was part of the problem probably. But what people tended to do is they tended to put two BNGs into the networking infrastructure. The assumption was that the service provider was going to provide video to the customers or their customers, and we would have an internet BNG and we would have a video BNG, and that video BNG would be associated with the television offering offered by that particular service provider. The reality is that video comes from everywhere. It normally comes, or very often comes through from the internet, so it is actually going through the internet BNG rather than the video BNG. And what we're seeing is service providers looking to perhaps alter their architectures to deal with this difference in traffic patterns that has become the reality. And because we're now able to integrate things like BNG functionality into carrier Ethernet devices, we're able to integrate things like CDN technology into carrier Ethernet devices, we're seeing the IP edge actually pushing further out into the network for consumer environments, and alongside that, we're seeing the CDN and that type of technology moving out as well. Net is that the aggregation network that in the past was typically a layer 2 only infrastructure now needs to support layer 2 and layer 3 services. Looking at mobile, we have some similar type, I won't say issues, but we have some similar types of characteristics. The mobile world of the past was very, very hierarchical in nature. We had the RNC or the 2G equivalent of it. We had TDM technology going from the cell sites to that RNC, and then we either went off into the circuit switching world or the packet switching world and hit the GGSNs and the SGSNs. And what we're seeing with the advent of LTE is really a decomposition of the entire mobile space from the, let's call it from the controller down to the base stations. We now have IP out at the base stations. We have a fairly complex set of relationships between the device or the base station and the network itself. It will be talking to the MMEs, which is the signaling component. It will be talking to the gateways, the S and the P gateways. And not in some instances, it will also be talking between base stations themselves over an interface called the X2 interface. These are complicated interactions. I can build them using layer 2 technology. I could build a VPLS type infrastructure in that aggregation network and allow everyone to connect up. But a lot of providers are actually looking at layer 3 technology to provide this type of connectivity. So I connect the base stations to a layer 3 VPN or multiple layer 3 VPNs, and then build the infrastructure to allow the connections to the S and the P and the MME type infrastructure, and also the X2 infrastructure. Again, it's kind of related to the fact that carrier Ethernet equipment will support both layer 2 and layer 3 services, and we can integrate things like security gateway functionality into those devices. So we can have a secure IPsec or appropriate security connection from the base stations, and then we go into a layer 3 infrastructure. So looking at how we anticipate, and this is quite an old slide, we're actually seeing this. We're seeing the layer 3 edge beginning to be pushed further and further out into the aggregation network. Perhaps not quite as far as I'm showing here, but certainly away from the traditional sort of BNG, RNC type sites where they've existed in the past. And we're also seeing that these infrastructures are being integrated together so we can create, layer 3s that go from here to the other side of the network, et cetera, et cetera. So the network is sort of changing in its sort of design and nature. So now I'm going to talk, and I'm going to change sort of subjects a little bit. I'm going to talk about core packet design and some of the challenges we see in that particular space. So again, another highly stylized picture, but what we see in sort of core designs from sort of 2000 to, maybe not today, but from 2000 to 2009 was a pretty hierarchical IP design. We tended to go IP directly onto 10 gig systems, typically via gray interfaces and transponders, and the scaling mechanism for these infrastructures was the use of bundles. And I know quite a few customers that have point-to-point connections between routers that have in excess of 30 interfaces in a bundle, be those 10 gig or 40 gig. What we have been hit with over the last couple of years is cost. A lot of discussion about whether this is the most cost-optimized way of building the network. And The other thing that is coming down the line is, what do we do about 100 gig DWDM? Because we know it's coming, and we know the fact that we've got a ton of bundled interfaces that we are having issues with the 10G environment, and that could be either through spectral exhaustion, or it could be the fact that the clients have considerably more bandwidth requirements than the actual underlying transport network can actually offer. So let's discuss very quickly, and I'm not going to dwell on this hugely in this presentation, but let's discuss 100G DWDM and core packet networking. So there's a lot of discussion about how 100 gig is going to go into the network and what it's going to look like. And I think one of the main things that I've seen over the last couple of years is that the assumption being that if I implement 100 gig DWDM, then I need to implement a OTN switching, TDM switching layer on top of it. And the second thing is that all client services, so IP, Sonnet SDH, ATM, and all of that stuff, are going to go through an OTN switching layer to access the DWDM layer. And I think there are a couple of reasons that people are putting that concept around. First of all, there's certainly in the early days of discussions about 100 gig DWDM, the assumption kind of was that if I'm going to upgrade a lambda, then I need to upgrade, if I'm going to upgrade a fiber, then I need to upgrade all the lambdas on that fiber and make them 100 gig, because 10 gig, 40 gig, and 100 gig will not sit together well. And even if I can put them together, I'm going to waste spectrum because I need a guard band between the different types of lambdas. The other one is that there is going to be a bandwidth mismatch between the server layer, the DWDM layer, and the client layers. Now, if we look at whether that is actually fact or fiction, all lambdas on a fiber need to be upgraded to 100 gig. That is actually fiction. We certainly, in most scenarios, I would say ultra-long haul environments may be the exception to this rule, but most scenarios we see in the European market space, 10, 40, and 100G will quite happily sit together on the same fiber, and I don't need to use guard bands between the actual lambdas. So there is absolutely no reason why I can't build a sort of heterogeneous DWDM infrastructure. The second one is the bandwidth mismatch between DWDM and the server layer. Now, I think that discussion depends at which or which client you look at. Perhaps for SDH, perhaps for ATM, that is a true statement. There are no 100 gig Sonnet SDH devices out there today, so I am going to have to go through an intermediate layer to get down to the DWDM layer. However, for packet networking, that is pretty well fiction. If you think about why 100 gig is coming in, 100 gig is coming in because basically the packet networks are consuming the DWDM lambdas that are available. And there are two reasons it's consuming them. One is because the bandwidths are going up, so I need to bundle them. So the client is going up. And as a consequence of bundling, I'm getting spectral exhaustion. So if I start to put my packet networks directly onto 100 gig, I'm actually going to solve both problems. I'm going to get better spectral efficiency. I'm also going to be able to match the client bandwidth closer to the actual transport bandwidth. And I just want to give you an illustration of where we are in terms of bandwidth on some of the really big networks out there. We have a US customer that has gone to 100 gig. They are currently on an 1100 gig bundle. So they have 1.2 terabytes between a pair of routers in their backbone network. So we're already seeing people actually having to bundle 100 gig connections to actually deal with the demands that they have within the network. So 100 gig does not mean you need OTN TDM switching, and I would put to you that in most cases, it's not everywhere perhaps within the network, but in most cases the packet infrastructure is going to continue as it does today to interface directly with the DWDM layer and will not go through an intermediate TDM switching layer. Let's now talk about core routing costs. This is a graph that was produced by Stu Elby from Verizon probably about 5 years ago, which basically showed a triangle, and it basically had photonic switching, so this is ROADMs, circuit switching, OTN, TDM, Sonnet SDH switching, and then packet switching at the top. And the sort of premise was that as you go up this layer, the cost actually of the solution increases. This graph has created a massive debate over the last couple of years, and that debate has primarily revolved around how I design my core packet networks. Do I use a combination of circuit switching and packet switching? I think everyone agrees that packet switching is required at the edge, but how I connect those edge devices together is really the debate. So it's caused a lot of debate, and I'm sure that if you guys have been to any of the transport conferences over the last couple of years, you will have seen people putting up models about the cost of different architectures. One of the things that I think has been largely ignored is actually the photonic switching piece at the bottom, and probably the reason it was ignored was because at the time this graph was drawn, or this is not a graph, is it? This triangle was drawn, the photonics layer was not a particularly flexible layer. It was a point-to-point DWDM infrastructure. And today, if I look at that photonic switching layer, it's actually a ROADM infrastructure. We've got the flexibility in the client interface. So it's something that we need to consider actually looking forward. And perhaps the debate is not about this bit here. It's actually, the debate is about the whole of the three layers combined together. So we miss a... Oops, there we go. So what was the debate about building the packet network? The left-hand side of this picture, I think it's same for you. Left-hand side of the picture shows, let's call it the traditional view of the world. The right-hand side of the picture shows the sort of transport hollow core type view of the world. And basically what we saw on the right-hand side is the concept was that we had routers around the edge, and we connected everything together using logical connections built from a transport infrastructure. And the transport infrastructure that people are discussing today is really using OTN cross connects to provide that connectivity. So those green boxes are OTN cross connects. So that's the debate on the actual architectural design. Just before I talk more about, sort of looking at that, the next piece that we need to think about is, what does the core routing infrastructure look like? And as I said, in the past, the core routing infrastructure has very much worked on the concept, I put the core box in and I gradually move it out to the edge. The downside of that is that there's an awful lot of functionality used on the edge that's not required in the core. So you make a capital investment up front to get benefits later in the life of the product. What we're seeing today across the industry, I would say, is we are seeing more core optimized solutions. And there are two ways to provide those optimized solutions. One is to provide it on a box level, and there are vendors out there that are doing that approach. The other is to provide it on a line card basis, and that's the approach that we're taking. So on CRS, as an example, you can get core optimized line cards, you can get peering line cards, you can get edge line cards, and you can mix and match those line cards to create the right solution. The reason that we believe that that's the right approach is that there are very few core-only boxes out there. There are generally some in the really, really big networks, but a lot of other networks around the place have a core box that's providing perhaps a peering connection, a core box that is providing high-speed PE capabilities. So we're seeing cost-optimized modular core routing solutions. So what do we see today? We see that triangle shrinking. We also see actually another thing that is quite important, which is those blue bubbles that interconnect the layers. Those blue bubbles that interconnect the layers are optoelectrical components, and those optoelectrical components are extremely expensive. I don't have time to go through it here, but as we go to higher and higher speed interfaces, the optics become more and more significant in the overall cost. So what we're seeing looking forward with 100 gig in particular is that we need to build an infrastructure that supports the bandwidth and the payload, etc. But we need to actually optimize the amount and the number of optoelectrical components that we see within the network. So let's keep moving. So I did a very quick model looking at different designs. The top picture shows a hierarchical solution, routers at the edge, routers in the core, and the bottom picture shows a bypass type solution. And what we have in terms of the top solution is the physical infrastructure looks like the logical infrastructure. In the bottom case, what we have is we have an infrastructure where we have a physical infrastructure and then there is a transport infrastructure laid over the top, and we have, in this particular case, a partial mesh, and what we're doing is we're bypassing the nodes in the middle, and we're using TDM switching to bypass those connections. What do we see when we run a model over a 5-year period? What we see is that by using bypass solutions, we move the introduction of 100 gig DWDM in the core forward. Why is that? Because we can't statistically multiplex across that network. The bypass solution requires more overall capacity because we need to be able to do worst case provisioning across the network. We do reduce the overall IP interfaces in the network, but the downside of that is that we increase the overall number of interfaces because we've got to have IP and OTN interfaces. So we see that actually, although a lot of people have said, well, circuit switching is cheaper in terms of port cost, when you actually put it into a networking environment and lay loads over that networking environment, it doesn't actually, those cost savings don't actually translate to real world savings. So I've talked about what not to do. How do we actually evolve the packet network? I would suggest to you that actually we use a combination of bypass and hierarchy. What we do in the core of the network is we use bypass. And so we get rid of that inner and outer core concept, but we keep hierarchy on the edge because hierarchy on the edge allows the network to build, to create a statistically multiplexed environment. If we're going to do bypass, don't do it using an electrical layer, use an optical layer, the photonics layer. So what we see is more meshing in the core with hierarchy on the edge of the network. How do we build the bypass, the photonics bypass? Well, we've got two options. We can put the short reach interfaces down to transponders onto the DWDM infrastructure, or we can integrate the transponders into the routers and then go down onto the photonics infrastructure. You'll notice that on these intermediate nodes, there are no OEO conversions, no optoelectrical components whatsoever. It's just a photonics cut-through. How do we integrate the photonics layer and the IP layer? We've got a flexible layer at the optical layer, or more flexible layer at the optical layer. We have a flexible layer at the IP layer. We get a load of benefits if we can start to integrate those two layers together. We've developed a technology called Nlight. We are building a multi-layer controller. I've called it an SDN controller, but a multi-layer optimization tool that will optimize the two layers together. So if the routers need more bandwidth, they can request it. If the routers need to restore a piece of optical bandwidth, they can initiate it. So what does that give us? It gives us the ability to remove inefficiencies, because we have a level of communication between the different layers. And I've shown 3 examples here. We have the ability to, if I strategically place transponders around the network, I have the ability to do a bandwidth on demand type solution. So I can put a connection where I have a heavy load and then remove it when the network no longer needs it. So I'm showing 3 examples. I can do re-optimization. I don't necessarily have to have live bandwidth in the network all the time. So I get a failure, I re-signal, and we go across a different path. And then perhaps a more advanced use case, I could potentially deal with a router failure by getting the site to actually rehome to another site within the network. Clearly that's going to have routing implications. We got to think about OSPF areas and all of those good things, but it's potentially something that we could look at, particularly in a single level ISIS or a single level OSPF area. So to summarize, how have things changed, or how are they going to change? 100 gig and beyond agile DWDM. Modular lean core routers in the core. Consolidated L2, L3 metro environment and core. Hierarchy at the edge, but lambda level bypass in the core, so more meshing within the core. Distributed data centers and peering around the network, perhaps only at the core sites, but perhaps even down at the regional levels of the network in some instances. Unified MPLS allowing us to create end-to-end L2, L3 connectivity from the metro to the core. 100 gig link bundles, and then integrated DWDM and Nlight technology between the optical and the IP layer. And then, let's go through that one. Just 2 very quick sort of last thoughts. What will the future look like? We see 100 gig DWDM infrastructure. We see IP MPLS technologies going down onto that. We also see OTN there. OTN switching has a role in next generation networks, no doubt about it, for things like private line services, support for Sonnet SDH onto 100 gig environments. But the key thing is that both the OTN switching layer and the IP MPLS layer will be clients of that 100 gig OTN, DWDM transport network. And just one last thought, what will the actual sort of services running on them and the revenues generated by those services look like? We see the L3 IP services running on IP MPLS technology. They are going to be the biggest bandwidth consumers. They are also going to be the biggest revenue generators. We're going to see traditional voice services migrate to IP MPLS technologies. We will see a set of L2 Ethernet services and private line services spanning both IP MPLS, OTN and SONET environments. But in terms of overall bandwidth, and perhaps, obviously it depends on the provider, but perhaps in terms of revenue, they will not be massive revenue generators. And I think we'll just go straight through that one. And that's me done. Thank you.
Thank you very much. Are there any questions? So now 5 minutes break. Oh, yeah.
Oh, sorry.
Since there was described this first, let's say, stage that we have ROADMs, optical switching, etc., and then we goes to the OTN, I got a little lost. What is really the strategy? Going to the electrical or optical layer of switching?
For IP environments, packet environments, where there is a need for very high bandwidth, we go directly to the DWDM layer.
Okay, but how it's realized in electrical or optical domain? What's your strategy?
I'm not sure I completely understand the question.
You have shown this ROADM and GMPLS capabilities can somehow merge the switching in the optical layer, and then the OTN and capabilities of understanding OTU frame and switching in electrical domain. So finally, I'm a little lost. What's your strategy? Switching in optical or electrical domain?
Let me just go back.
It's a general feeling of the last 20 slides.
It's switching in the optical domain. So the routers will interface directly with the optical domain, and there will be an interaction between the optical domain and the packet switches. But there's also no reason why there couldn't be an interaction between an OTN switch and the optical domain. But fundamentally, the packet switching infrastructure will interface directly to the optical domain. The OTN switching infrastructure will interface directly to the optical domain.
Okay, so it means that we will definitely use the ODU framing to switch in between nodes.
No, you will put the traffic onto a you will put the IP traffic onto a lambda that is ODU framed, but it's not switching between. There is no switching component between those nodes.
Okay, so the OTN that was mentioned on the slides, that's one of the strategy. Actually, it's not going to be supported in this stage. Just reservation of the lambdas based on the request from the router, yes?
So we will be able to signal from a packet switch that sits here to an optical infrastructure to get an end-to-end lambda between those two devices.
Okay, but you have mentioned this G709 standardization, which is going a totally different way. It is allowing to switch within the ODU frames and no need to reserve anymore because you can dynamically actually reserve on the demand. So this is kind of going backwards 2 years.
No, this is going forwards.
Sorry,
you're going back.
But we have to go to the next presentation.
Okay.
But you can talk
Thanks.
with Simon Spraggs during the break. So now I invite you to 2 minutes break. And thank you very much, Simon Spraggs, for the presentation.